Imagine, if you will, a single butterfly, its wings a delicate mosaic of vibrant colour, flitting gracefully through a sun-dappled forest clearing. Each gentle beat of its wings stirs the air, creating tiny, almost imperceptible eddies and currents that soon dissipate into the wider atmosphere. To the casual observer, this is merely a fleeting moment of natural beauty, an ephemeral dance, seemingly insignificant in the grand theatre of nature. Who could possibly imagine that such a minuscule disturbance, a mere whisper of movement from such a fragile creature, could play any conceivable role in shaping events far grander in scale, perhaps even on distant continents? Yet this very notion, this fascinating proposition, lies at the very heart of one of science's most intriguing and thought-provoking concepts, suggesting a world far more intricately connected than we often perceive. Consider for a moment a tiny pebble, dislodged from its precarious perch high on a rugged mountainside by a gust of wind or a passing animal. It begins to roll, a solitary traveller embarking on an unplanned downward path. As it tumbles, it might nudge a slightly larger stone, which in turn disturbs others in its wake. Gradually, a small collection of moving rocks gathers momentum, growing from a trickle into a stream, then perhaps a torrent of debris. What began as an almost insignificant event, the almost silent motion of one small, unnoticed pebble, could potentially culminate in a thundering landslide, an immense release of energy dramatically reshaping the very contours of the landscape below. This powerful analogy helps us begin to grasp the profound idea that truly small beginnings can indeed lead to monumental consequences. This captivating idea isn't merely a flight of poetic fancy or a quaint metaphor designed to amuse. It is a concept with surprisingly deep and significant roots firmly planted in scientific understanding and meticulous observation. It directly challenges our everyday intuitive assumptions about cause and effect, where we naturally expect large outcomes to stem from equally large and obvious causes. But what if the intricate machinery of our world, the complex systems that govern everything from weather to ecosystems, operates on principles where the almost immeasurably small can, under the right confluence of conditions, blossom into something truly transformative and of monumental importance? This perspective opens up an entirely new and fascinating vista for understanding the complex systems that govern our planet. The incredible journey towards comprehending this profound interconnectedness and the power of minute influences did not commence in the untamed wilderness of a vast, unexplored jungle, nor did it begin on a storm-tossed sea under dramatic skies. Instead, the seeds of this revolutionary idea were sown within the rather more sterile and controlled confines of a scientific laboratory. It all started with a dedicated researcher, an early room-sized computer chugging away at its calculations, and a completely unexpected, almost accidental observation. This serendipitous moment, a tiny anomaly in a routine numerical simulation, would send ripples of understanding outwards, much like the very effects it described, forever changing how we view the limits of prediction and the inherent nature of complexity. During the early 1960s, a brilliant and inquisitive meteorologist named Edward Lorenz was deeply engrossed in his pioneering work at the prestigious Massachusetts Institute of Technology. He was utilizing what was then considered a state-of-the-art computer, a Royal McBee LGP-30, a cumbersome machine by today's standards, to painstakingly model and attempt to predict global weather patterns. His ambitious goal was to create sophisticated mathematical simulations that could forecast how atmospheric conditions might evolve over extended periods. Lorenz would meticulously input a series of initial conditions, fundamental data points such as prevailing temperatures, barometric pressures, wind speeds, and levels of humidity, into his complex equations, hoping to discern how the weather might unfold based on these crucial starting values. One fateful day in the winter of 1961, a day that would unknowingly alter the course of scientific thinking, Lorenz decided he wanted to re-examine a particular weather simulation he had run previously. To save valuable and expensive computer processing time, a significant constraint in those early days of computing, instead of initiating the entire complex sequence from the very beginning, he chose to input the numerical data from a printout that had been generated midway through the earlier, longer run. The printout displayed these crucial numbers rounded to just 3 decimal places, for instance, a value like 0.506. His computer's internal memory, however, stored these figures with a greater degree of precision, typically to 6 decimal places, such as 0.506127. This minute difference, less than 1 part in 1,000, seemed utterly inconsequential. What transpired next was entirely unforeseen by Lorenz and utterly astonishing to him as a scientist dedicated to uncovering predictable patterns. Initially, the new simulation, the one started with the slightly rounded numbers, mirrored the original simulation's projected path almost perfectly, behaving just as he had anticipated. However, as the computer continued its complex calculations, the two simulated weather patterns began to diverge. At first, the differences were incredibly small, almost unnoticeable, buried within the vast data sets. But progressively, inexorably, they grew larger and larger, eventually leading to completely different, wildly divergent long-range weather forecasts, where one might predict sunshine and calm, the other storms and upheaval. Lorenz was profoundly struck by this dramatic and unexpected outcome. He quickly realized that this extreme sensitivity to the tiniest variations in initial conditions was not some peculiar flaw in his model, but rather a fundamental characteristic of complex, dynamic systems such as Earth's vast and turbulent weather. He famously encapsulated this groundbreaking idea in the title of a scientific presentation he delivered in 1972. Predictability: does the flap of a butterfly's wings in Brazil set off a tornado in Texas? This wonderfully evocative question gave birth to the popular term, the butterfly effect, beautifully illustrating how a seemingly insignificant local event could trigger a chain reaction leading to major, widespread consequences. The butterfly effect, while a beautifully poetic and accessible phrase, serves as a wonderfully descriptive metaphor for a core scientific principle known more formally as sensitive dependence on initial conditions. This principle is absolutely fundamental to the branch of mathematics and physics called chaos theory. It is vitally important to understand that chaos theory doesn't imply complete randomness or utter unpatterned disorder. Rather, it studies systems that are inherently complex, nonlinear, and dynamic. Systems whose behavior can appear erratic, but is actually governed by underlying deterministic mathematical laws. Chaotic systems are remarkably ubiquitous in the natural world, appearing in phenomena from the turbulent flow of fluids and the intricate patterns of smoke rising to the fluctuating populations of animal species and the rhythmic beating of a human heart. While these systems are fundamentally deterministic, meaning their future state is theoretically determined by their initial conditions and physical laws, a critical practical limitation arises. The perfect knowledge of these initial conditions is an unattainable ideal in any real-world scenario. Even the most minuscule error in measuring the starting state will be amplified exponentially as the system evolves over time. Imagine attempting the delicate feat of balancing a pencil perfectly upright on its point. The slightest tremor in your hand, the faintest current of air, even vibration from a distant footstep will determine the direction it tumbles. And once that initial lean begins, its path of falling is largely set, irretrievably so. Earth's vast weather systems are infinitely more complex than a simple falling pencil involving countless interacting variables. This sensitivity is precisely why detailed weather forecasts become less reliable the further into the future they predict. This unpredictability in chaotic systems stands in contrast to simpler, linear physical systems, such as predicting the orbital path of Mars or Jupiter around our Sun. In celestial mechanics, the dominant gravitational forces allow for highly accurate long-term predictions. For chaotic systems, however, the future trajectory is tethered to its precise present state. A tiny alteration in the here and now can lead to a vastly different there and then, reshaping scientific approaches to natural phenomena. The profound implications of the butterfly effect extend far beyond atmospheric science and weather prediction. Consider the delicate balance within a natural ecosystem. The removal of a single species can trigger an unforeseen cascade of consequences that ripple throughout the entire food web. A key predator species might vanish, leading to an unchecked overpopulation of its primary prey, which could then decimate certain plant species through overgrazing, ultimately altering the habitat conditions for a multitude of other dependent organisms in significant ways. Similar principles of sensitive dependence can be readily observed in diverse scientific fields such as chemistry, where minute variations in the initial concentrations of reactants or subtle fluctuations in ambient temperature can dramatically alter the specific chemical products that are formed or significantly change the rate and overall efficiency of a particular chemical reaction. Even within the highly complex dynamics of human societies and global economic systems, analogous patterns of behavior frequently emerge. A seemingly minor piece of misinformation, a rumor, can rapidly escalate, potentially causing significant market fluctuations or influencing broad social trends in entirely unexpected ways. The groundbreaking discovery of the butterfly effect delivered a significant challenge to the long-held classical deterministic worldview that had largely prevailed since the revolutionary era of Sir Isaac Newton. This older, more mechanistic perspective posited that if one could ascertain all the fundamental laws and precisely measure the initial state, then the future could be predicted with absolute certainty. Chaos theory, however, unveils that even with perfectly known deterministic laws, perfect long-term prediction is often unattainable for most complex, real-world systems due to this inherent sensitivity. Ultimately, the concept of the butterfly effect imparts a crucial lesson about the true nature of our profoundly interconnected world. It vividly underscores the potential impact of even our seemingly smallest and most inconsequential actions. While we may never definitively know if a single specific act will dramatically alter global events, the powerful idea serves as a constant reminder that we are all integral components of a vast, intricate global system. This deeper understanding should foster responsibility and mindfulness in all our choices and behaviors.